So firstly we have the program counter register. Now the purpose of the program counter is it points to the next instruction that we want to execute. So this one's very handy for allowing us to keep track of where we're up to select what code we're going to execute next, and particularly when we're performing jumping, it'll actually point to the new location that we're actually jumping to. Our SP, or stack pointer, always points to the top of the stack. So remember, our stack is a data structure where we can stack extra things onto it, and they always go on at the top and they always come off from the top. So it's last in, first out. The stack pointer is always pointing to the top element of it, which is in fact the last thing that we've put onto the stack. When we're running subroutines later on, when we're generating interrupts later on, the way that we get back to where we were previously is we put them on the stack before we enter our subroutine or our interrupt. Our next one is the status register. Now the status register is a collection of flags and settings, and essentially we want to treat these as individual bits. Some important ones are the 0 flag, the negative flag, and the carry flag. So gives important info on state of system. And ALU results. We have the constant generator, which essentially generates key constant values which are commonly used. Some examples would be 1, 0, and 2. And GP stands for general purpose. And these are essentially accumulators that you can put whatever you want in them. So you can do computation, storage, logical operations, essentially whatever you want. Our second question asks us about different addressing modes and where they might be most appropriate to use in different situations. Now, first one, we're considering a cipher that encrypts data based on a lookup table in memory. And let's assume for a moment this is like a Caesar cipher or something like that, where we have an offset, and that offset is based on the particular number that we're trying to encode. So the classic way we'd implement something like this is with indexed addressing, because we have a register, for example R5, and we offset from that register a certain number, so it might be 5. Next one, we need to load a constant number into a register. Well, whenever we're adding a constant in, we're using our hash symbol. So we're doing an immediate form of addressing. Next, we've got something, piece of hardware, peripheral hardware, never designed to move in our memory map. We could do symbolic, or we could do absolute. So we might do something like this, F800, we're looking at absolute. Here we're using pointers, so we're referring to data by reference rather than by value. Now the way pointers work is essentially they rely on an indirect form of addressing. So we have our at R5, we look at what's stored in R5, so there might be 0xF802 in R5, and then we look in that memory allocation what's stored there. That's what we'll be looking at. So we're using indirect form of addressing. And finally, we're doing some small calculations between registers. I've kind of almost given you the answer there. It's register addressing. So we might be doing add R6 to R12, for example. Okay, in this one we're looking at identifying the source and destination addressing modes for each of these different examples. So we see for this first one, our source addressing mode is going to be immediate because we've got the hash there. And our register, or our destination addressing mode is register because we're referring to a specific register. Next one, we're using our brackets there. So this is index addressing, and once again register. Our next one, we've got our ampersand there, so we're using absolute addressing. And here we don't have anything. Don't be tricked, it's not immediate addressing. If we don't have anything there, it's symbolic. Next we've got our at symbol, so this will be indirect. And we've got another index addressing mode, an indirect auto increment, we know it's the auto increment because of our plus sign there. Once again, another register. Here we're comparing a couple of things rather than moving around before, but look, they're both registers. Our final one is symbolic as before because we don't have any hash symbol there or any ampersand symbol as we had previously. So this one is a bit meaningless for source and destination because it's not really a single or a double operand instruction, but what we're dealing with is symbolic. So for this final question, what we're going to do is need to write where these instructions actually occur in memory, and that will tell us where our memory addresses are. So we're told our memory locations start at 0xFC00, so we need to count on from there. So 0xFC00, 0xFC02, 0xFC04, and so on. And now we have to write where what instructions are stored here. So we'll put here it's the memory. Our memory address and our code. So the first one 0x4037 and 0x0018, and just note that that's one instruction, so it's a longer instruction than normal. 0x4036 0x0005, once again one instruction, 2 words. And our remaining ones are smaller, so 5607 0xe337 0x9607 0x3DEE. Okay, so once we've done that, we can write down our value of the program counter. So for the purpose of this, we're going to assume that we're executing the instruction that we write the program counter down next to, and so we want to point to the next instruction. So when we're executing this first instruction, this one up here, we're going to be pointing to the next instruction, which starts at FC04. When we're executing that instruction, point to the next instruction, FC08, and now we only jump up by 2, FC0A, 0xFCOC, 0xFCOE, and in this case we're actually jumping back to the start again. So rather than being the next instruction sequentially, we're going to be jumping back to FC00. Okay, then what we want to do is show the changes in the registers R6 and R7. So this first one will move 24 to R7, so R7 equals 24. Next one moves 5 to R6, so R6 is equal to 5. We're adding R6 to R7 and storing the result in R7. So R7 is equal to 29. We're then inverting R7, so swapping all the bits. So R7 is equal to 0xFFE2. So if the bit was a 1, it becomes a 0. If the bit was a 0, it becomes a 1. We want to compare them. So we don't actually update anything when we compare them, and we don't actually update anything on a jump either.